Evaluation of border irrigation. Why do we evaluate an irrigation system? We do it to check its current performance and to suggest modifications which can improve its performance. The principal objective of evaluation is to identify alternatives that may be both effective and feasible in improving irrigation performance. For example, if the length of this border is too long, it may result in non-uniform distribution of water. If the inflow rate is not high enough, it may result in deep percolation losses at the inflow end, and depth of application at the lower end will be less than the required depth. So, an evaluation may reveal that application efficiency could be improved by limiting the duration of irrigation, uniformity may be improved by adjusting the flow rate, modifications in field length and slope may be required for minimizing losses in certain cases. So once a thorough evaluation of an irrigation system is completed, we can offer certain suggestions to improve the performance of the irrigation system. And for a thorough evaluation, we need certain measurements like inflow discharge, advance and recession of water, tailwater discharge, moisture deficit prior to irrigation, volume of water on soil surface at various times, and indication of infiltration characteristics. Let us quickly recall some of the basics of border irrigation. In a border irrigation, field is divided into a number of long parallel strips, generally 3 to 15 meters in width and 60 to 300 meters in length, separated by small border ridges or low dikes of about 15 centimeters. After sufficient water is applied to one strip, irrigation stream is turned into another strip. If the discharge is high enough in the field channel, the strips can be irrigated simultaneously. Otherwise, they have to be irrigated one by one. A specific requirement is that the longitudinal slope, that is, the slope along the length of the border, should be uniform and the transverse slope should be zero or negligible. Now, this method is suitable for close growing crops like wheat, barley, fodder crops, and legumes. Now, these are some of the suggested values of length and slope for different types of soil. For coarse textured soil like sandy and sandy loam soils, the length ranges from 60 meters to 120 meters. Whereas in fine textured soils like clay loam and clay soils, the length ranges from 150 meters to 300 meters. In case of slope, high values of slopes are permitted in sandy soils up to 0.60%. And in case of clay soils, high slopes are not permitted. Okay, the value of slope ranges from 0.05% to 0.20%. Now these are the values of stream sizes to suit varying soil characteristics and border slopes. For sandy soil, high value of discharge is permitted, okay, 10 to 15 liters per second. Whereas in case of clay soil, the flow per meter width of border strip is 2 to 4 lps. Now this is the most important part of this lecture, hydraulic phases of irrigation. The first phase is the advanced phase. There are four phases. The first phase is the advanced phase. It is the time interval between the start of irrigation and arrival of advancing front. Okay. And once this wetting front reaches the end of the border, the advanced phase ends. And then begins the wetting phase. It is the time interval between the end of the advanced phase and cutoff of inflow. The inflow has not yet been cut off, so the wetting phase is going on. And once the inflow is cut off, the depletion phase begins. It is the time interval between cutoff and complete disappearance of water from inflow end. And the final phase is the recession phase. It is the time to recede from all points in the border starting from end of depletion phase. So once water from all the points has disappeared, the recession phase ends. The first phase is the advance phase. When water reaches the end of the border, the advance phase ends. Then begins the wetting phase, which continues till the time of cutoff. Okay. Then starts the third phase, which is the depletion phase, which ends when water disappears from the inflow end. Okay. And this is the final phase, the recession phase. It continues till water has disappeared from all the points in the border. And the time between the advance curve and the recession curve, okay, is called the opportunity time. Okay, we'll study more about opportunity time later in this lecture. Now, which factors affect the performance of a surface irrigation system? Factors like infiltration, slope, hydraulic resistance, required amount of application, geometry parameters, unit flow rate at the head end of the channel, time of cutoff, and length of border or furrow. We will go through these factors one by one. Infiltration. It is one of the most important factors. It is necessary to determine the parameters of infiltration before the evaluation of irrigation is carried out. Okay. And to obtain the infiltration parameters, we need infiltration data, which can be obtained by conducting double ring infiltrometer test at various locations in the field. In this figure, you can see that infiltration rate decreases with time and cumulative infiltration increases with time. Okay, and in this lecture, we will be using the Kostiakov's equation and the modified Kostiakov's equation. This is the modified Kostiakov's equation. Z is equal to kT raised to A plus F0 multiplied by T. Okay. K and A are constants. F0 is the final steady state of infiltration. It is also called the basic intake rate. Knowledge of infiltration characteristics of the soil is critically important for evaluation, design, or management of a surface irrigation system, without which it is very difficult to accurately judge system performance, application efficiency, and uniformity. Infiltration varies spatially as well as temporally. So, infiltration tests should be carried out at multiple locations. Okay, later in this lecture, we will solve a couple of examples in which we will determine the infiltration constants. Channel bed slope. Yes, if the slope is too high, it causes scouring. If the slope is low, then the advance rate will be slow and it will result in inefficient irrigation. Manning's roughness coefficient. Okay, it's a measure of resistance effects that flow will encounter. Okay, as it moves down furrow, border, or basin. Okay, it's a representation of the effect of roughness of the physical boundaries of the flow and cultivation practices. Okay, for bare soil, The value of n is 0.04. For dense crop, it is 0.25. So it affects the performance of the irrigation system. Okay, so Manning's N has pronounced effect on the hydraulics of the surface irrigation and hence on the efficiency. We will not be using Manning's roughness coefficient in this lecture. Okay, the examples which we will solve in this lecture does not include the roughness coefficient, but later we may use it. Required amount of application. Well, this is a good example of non-uniform distribution of water. Near the inflow end, there are deep percolation losses. The actual infiltrated depth is much greater than the required depth. Okay, and at the lower end, okay, at the downstream end, the infiltrated depth is less than the required depth. So one must first determine the required depth. Now, required depth represents the amount of water that needs to be stored in the crop root zone per irrigation to sustain normal crop growth. The crop type, stages of growth, presence or absence of shallow water table, and limiting soil horizons, among other things, determine the effective crop root depth. Soil type is the factor that determines how much water can be stored per unit depth of soil. Okay, and this factor will be used in calculating the efficiencies and uniformity. Unit flow rate. Well, it affects the advance rate to a significant degree and also recession, but to a lesser extent. Now, in coarse soils, okay, if large streams are required to spread water rapidly. In second or third slide, uh, I showed you a table in which high discharge rates were suggested for sandy soil, right? So large streams are required to spread water rapidly. Otherwise, deep percolation losses are caused at the upper side. Okay. Whereas in fine soil, smaller streams for irrigation are required. Okay. In that table, the flow per unit, the unit flow rates suggested was 2 to 4 LPS, liters per second for clay soil. So smaller streams are required, otherwise deep percolation losses at the lower side and runoff will be caused. Unit flow rate is expressed in liters per second. Okay, it is usually expressed in liters per second per meter width of border. Now channel length. It should be determined considering the soil type, method of irrigation and from previous studies. And there always exists a certain optimal channel length that would that would minimize the irrigation water losses, yet results in acceptable levels of adequacy and uniformity. Okay. Cutoff time. Cutoff time is the time at which supply is turned off, measured from the onset of irrigation. The ideal time of cutoff occurs when the infiltrated depth in the least watered portion of the field is equal to the irrigation requirement. So one has to conduct a number of experiments and then determine the ideal cutoff time so that high efficiency can be achieved. The most important effect of cutoff is reflected on the amount of losses, deep percolation, and surface runoff, and hence efficiency and adequacy of irrigation. If the if the cutoff time is too late, it might result in runoff losses, deep percolation losses, and if the cutoff time is too early, it will result in inadequate amount of irrigation. Now, Kostiakov's infiltration equation. Kostiakov's infiltration equation is Z is equal to KT raised to A. Z represents the cumulative infiltrated depth. K and A are constants. And in this lecture, we will do a couple of examples to determine the value of K and value of A. Okay, and if differentiation of this equation is carried out, we'll get infiltration rate. Okay, there are many forms of Kostiakov's equation in different books, but we'll be using this first form. Okay, infiltration rate can also be expressed in this way, kT raised to minus n, and if it is integrated, we get the cumulative infiltration depth. Okay, but this in the problems that we solve, we'll be using the first form, Z equal to kT raised to A, okay, which represents cumulative infiltration depth. Modified Kostiakov equation, also Lewis-Kostiakov equation, is expressed in this form: Z is equal to kT raised to A plus F0 T. F0 is the final rate of infiltration. Infiltration rate is I is equal to AKT raised to A minus 1 plus F0. We will be using Kostiakov's infiltration equation of this form, and we will determine constants K and A in this problem. Now, infiltration data obtained after conducting the double ring infiltrometer test is given. Determine the values of infiltration constants K and A of the Kostiakov's infiltration equation. Now, the infiltration data has been obtained. Okay, at 5 minutes, the accumulated infiltration was 1.8 centimeters, and at 130 minutes, the accumulated infiltration was 12.6 centimeters. Now, using this data, we will obtain K and A. Taking log on both sides, we will get an equation of this form: log Z equal to log K plus A log T, which is similar to the straight line equation y equal to C plus mx. Now, the x-intercept will be log K and slope will give us A. Okay. Now plot log Z on y-axis and log T on x-axis. Okay. Take log values of accumulated infiltration, plot it on y-axis. Take log values of time and plot it on x-axis. You will get a straight line and equation of straight line. Okay, y equal to 0.5793 x minus 0.1141. Here the x-intercept is log k, so log k is minus 0.1141. On taking antilog, we will get the value of k. K is 0.769. A is the slope, which is equal to 0.579. So we will get the Kostiakov's infiltration equation: Z equal to 0.769 T raised to 0.579. Okay, where Z is in millimeters and T is in minutes. Alternatively, you can directly uh, use this trend line in power form. Okay, you can plot y-axis and x-axis in Excel and select trend line of power form. So you'll get equation of this form: y equal to 0.7689 x raised to 0.5793. Okay, so directly you can obtain k and a. K is 0.769, A is 0.579, and our Kostiakov's infiltration equation with the values of K and A is Z equal to 0.769 T raised to 0.579, where Z is in millimeters and T is in minutes. Now, infiltration data has been provided. Now we have to determine basic infiltration rate F0 and values of infiltration constants K and A of the modified Kostiakov infiltration equation. Okay, cumulative infiltration is given in millimeter units. Okay. Now the modified Kostiakov's equation is Z equal to KT raised to A plus F0 T. Okay, T is time, K and A are constants. F0 is the final rate of infiltration. First, we have to plot last 4 to 5 data of infiltration. Okay, we will first determine the value of F0. Now this is the final rate of infiltration. It is the steady rate of infiltration which occurs after a long period of time. So we will plot last 4 to 5 data of infiltration, okay, on y-axis and time on x-axis. And then we can obtain F0 by determining its slope. Uh, as you can see, we have obtained a straight line because uh, after a long period of time, the rate was almost steady. So we have obtained a straight line, uh, and the slope of this equation y equal to 0.0288x plus 22.746 is our final rate of infiltration, okay, which is equal to 0.0288 millimeters per minute. Okay, this is the final rate of infiltration, or you can also say basic intake rate. So F0 of the modified Kostiakos equation has been obtained. Now we will determine K and A. Once again, for obtaining F0, we have to plot last 4 to 5 data of infiltration on y-axis and time on x-axis. And the slope of the line will give us the value of F0. Okay. Now, Z is equal to KT raised to A plus F0T. So, Z minus F0T is equal to KT raised to A, taking log on both sides. Now, this equation is similar to the straight line equation, y is equal to C plus mx. Now, we will plot log Z minus F0T on y-axis and log T on x-axis to obtain the value of K and A. Okay, it will give us a straight line. Okay, and log K is 0.6218. So K will be 4.186. K is 4.186 and A is the slope, which is equal to 0.256. Our modified Kostiakos equation is Z equal to 4.186 T raised to 0.256 plus 0.0288 T. Okay, Z is in millimeters and T is in minutes. Alternatively, you can directly use the trend line in power form. Okay, so you can directly obtain the value of K and A. K is 4.186 and A is 0.256. Again, we'll obtain the same equation. So this is how we obtain the constants of modified Kostiakos infiltration equation. Now, infiltration opportunity time. It is the difference between the time the waterfront reaches a particular point along the border or furrow, okay, which is the advance time, right? It is the difference between the time the waterfront reaches a particular point along the border or furrow and the time at which tailwater recedes from the same point. It's called infiltration opportunity time. Okay, so it is the difference of advance and recession time. So infiltration opportunity time at any point along the border or furrow is the distance between the advance and recession curve. Okay. At point A, advance time is 15 minutes and recession time is 52 minutes. So we can obtain opportunity time like this: 52 minus 15, which is equal to 37. Okay, recession time minus advance time. Similarly, we can obtain infiltration opportunity time for other points. If advance and recession curves are nearly parallel, It means water distribution is uniform. Okay. It means that most of the points have obtained similar infiltration opportunity time, okay, or contact time. Now this is a border, and as you can see there are markers or posts placed along the border. Okay, so how can we obtain infiltration opportunity time in field, okay, while irrigation is going on? Okay, first you have to place the markers at regular intervals along the border, and then you have to note the advance and recession time at each post. For example, at this post the advance time is 12 minutes, okay, 5 minutes. Okay, water reaches this point at 5 minutes, and it reaches post 2 after, let's say, 20 minutes. Okay, and then you also have to note the recession time, and then contact time or the infiltration opportunity time can be calculated. Okay, it is equal to recession time minus advance time. Now infiltration opportunity time will be used in the infiltration equation to calculate the irrigation depth applied. We will use this infiltration opportunity time as T in our Kostiakov's infiltration equation, Z equal to KT raised to A, and there T will be equal to infiltration opportunity time. Okay, and it will give us the irrigation depth. Now a farmer irrigated an open-ended border of 100-meter length, 5-meter width and slope of 0.0025 with the available discharge of 3 liters per second. The required irrigation depth was 10 centimeters. The irrigation started at 6 a.m. and stopped at 12:20 p.m. Determine the depth of irrigation provided by the farmer and application efficiency. Okay, so there is an open-ended border, okay, of 100 meters length, 5 meters width, and the discharge here is 3 liters per second. The required irrigation depth is 10 centimeters. Okay, so when the farmer irrigated, the required irrigation depth was 10 centimeters. He started irrigating it at 6 a.m. and stopped it at 12:20 p.m. Now let us see whether the farmer irrigated this border efficiently or not. Okay. Now double ring infiltrometer test was conducted and infiltration parameters for the Kostiakov's equation were obtained before the irrigation. We already discussed the methodology which we can use to obtain the infiltration constants. Okay, so we conducted the infiltration test and we obtained the constants. So our Kostiakov's equation is Z equal to 30 T raised to 0.75. Okay, where Z is in millimeters and T is in hours. And here you can see posts were placed at 10-meter length along the border. Okay, so at every 10 meters a post was placed. Okay, so time of advance and recession were noted during the irrigation. At the first post, it took water to reach the first post 2.1 minutes. Okay, water reached the second post at 4.24 minutes, and after 35 minutes, the water reached the sixth post. Okay, the time of recession was also noted. Now we can obtain infiltration opportunity time using recession time and advance time. Now this is the advance curve. Okay, and this is the recession curve, and difference between them gives us the infiltration opportunity time. Okay, it is equal to recession time minus advance time. Now, infiltration opportunity time to obtain required irrigation depth. The required irrigation depth is 10 centimeters, right? So, what is the infiltration opportunity time to obtain this required depth? How long should the water stay in contact with with some points along the border due to which we can obtain the infiltration depth of 10 centimeters. Okay, what should be the contact time that gives us 10 centimeters of depth? So we have rearranged this equation. T required is Z required divided by 30 raised to 1 divided by 0.75. Z required is the required irrigation depth. It is 100 millimeters. Okay, as this equation is in this form, okay, Z is in millimeters. We will use Z required equal to 100 millimeters. So we will get the required opportunity time of 4.98 hours, which is equal to 298.8 minutes. Okay. So if at any point water stays there for around 5 hours or 4.98 hours, we will get irrigation depth of 100 millimeters. Okay, if the infiltration opportunity time is 4.98 hours, then the irrigation depth will be 100 millimeters. If the infiltration opportunity time is less than this, then required depth will not be obtained. Okay, required depth will be less than 100 millimeters. And if infiltration opportunity time is more than 5 hours, let's say 6 hours, then Z required the irrigation depth will be more than the required depth. Okay, so if opportunity time is 298.8 minutes, required irrigation depth of 100 millimeters will be obtained. Okay, now let us calculate the opportunity time from the advance and recession time. Okay, in our case, intake opportunity time is much more than required. Required is 298.8 minutes. This is sufficient for providing depth of 100 millimeters. Okay. Now recession minus advance time gives us intake opportunity time or infiltration opportunity time. It is 381.9 minutes at the inlet end. It is 387.2 at the first post. Okay. At the eighth post, it is 339.5 minutes. So we can say that excess irrigation has been provided on at these points, right? Okay, at the last point, infiltration opportunity time is less than the required opportunity time. Okay, so it will give us slightly lesser depth than the required depth. Okay, so now we will use this equation. Z is equal to 30 t raised to 0.75. Okay, Z equal to 30 t raised to 0.75. T is 381.9 minutes, which is equal to 6.37 hours. So, substituting the values of T in this equation one by one, we will get depth. Okay. In the first case, depth is 120.2 millimeters. So, it is 20.2 millimeters more than required. And average uh, infiltrated depth is 114.6 millimeters. Okay, average of all these depths. Now, as I as mentioned in the problem, the required depth is 100 millimeters, and this is our infiltrated depth. Okay, it's 120 mm, around 120 mm, and here it is less than 100 millimeters. Okay, we've plotted infiltration depth here along the distance. So we are giving more irrigation than required. Okay, applied depth is 120, 121, 122. Required depth is 100 millimeters. So deep percolation depth will be 120.22 minus 100. Okay, this excess depth is the deep percolation depth. Okay, here there will be no deep percolation. Okay, at this point, the deep percolation is 2.5. It is 10.1 here. Okay, and the average deep percolation depth is 15.3 millimeters, and this is the depth stored in the root zone. This is the useful depth. Rest of it uh, is lost as this deep percolation. Okay, so out of 120, 100 millimeters will be stored. Okay, this is the useful depth. In the last case, the stored depth will be equal to 92.77, slightly less than the required depth. So depth stored is 99.35. So we have provided the required depth along the entire length except the last part. Okay, but we have given excess of water. Now inflow volume is equal to discharge multiplied by time t. Okay, now discharge was already given. It was 3 liters per second, which is equal to 0.18 meter cube per minute. And time, okay, what was the cutoff time? Cutoff time was 380 minutes. Okay, remember the irrigation started at 6 a.m. and it was stopped at 12:20 p.m. Okay, am I right or wrong? Let me check. Yes, 12:20. So which gives us cutoff time of 380 minutes. Okay, cutoff time is 380 minutes. So in 380 minutes, how much inflow volume was provided? Okay, so discharge multiplied by time will give us the total inflow. It is equal to 68.4 meter cube. Okay, 68.4 meter cube. This will be useful later while calculating efficiency or uniformity. Irrigation volume infiltrated is the depth applied multiplied by area of border, right? The average depth applied was 114.6 millimeters, right? It was 114.6, yes. And area of border is length multiplied by width, which is equal to 500 meter square. So the total volume infiltrated was 57.3 meter cube. Okay. So total inflow volume was 68.4 meter cube. Infiltrated volume was 57.3 meter cube. Irrigation volume stored is equal to depth stored multiplied by area of border. Now depth stored, it means the useful depth, okay, which is almost equal to 100 millimeters, except the last point, the depth stored was 100 millimeters. We found the average and the average was 0.9935 meters, right? Okay, this should be 0.09. Okay, this is a mistake here. It is equal to 0.09. Let me correct it. Okay, 0.09935 meters, and area as calculated before is 500 meters square. So the volume of irrigation stored was 490.49.67 millimeters. Okay, so depth stored, the useful depth stored multiplied by area of border. Okay, so volume stored is equal to 49.67 meter cube. Okay, now water application efficiency is the volume of water stored in root zone divided by volume of water delivered. Okay, application efficiency is V stored divided by V in, okay, which is equal to 49.67 divided by 68.4. Okay, and it gives us the efficiency of 73%. So water application efficiency is 73%. Now let us calculate the water distribution efficiency. Now ED in percentage is equal to 1 minus Y divided by T. Y is the average deviation in depth of water infiltrated from average depth infiltrated during irrigation. And D is the average depth of water infiltrated during irrigation. Now we already know the average depth. Okay, it is 114.64. And average deviation is calculated by subtracting depth from average depth, right, and take its absolute form. So this is the deviation from the average value, and the average deviation is 7.1 millimeters. Okay, D is the equal to Z average, which is 114.64. Now substituting the values of Y and D in the equation of water distribution efficiency, and then we will get the water distribution efficiency. It is equal to 93%. Okay, so we have calculated the water application efficiency as well as water distribution efficiency. Now we have calculated this before. Okay, the total inflow volume was 68.4 meter cube, infiltrated volume was 57.3 meter cube, stored volume was 49.67 meter cube. Okay, runoff and deep percolation will be obtained. Okay, it is 11.1 meter cube and 7.63 meter cube. But how did we obtain this value? Let us find out. Okay, now inflow volume is infiltrated volume plus runoff. Remember, the border is open at the end, so there will be some runoff volume. Now V in is equal to V infiltration plus V runoff. Okay, so inflow volume is infiltrated volume plus runoff volume. Therefore, the runoff volume will be equal to infiltrated volume, inflow volume minus infiltrated volume, which is 11.1 meter cube. Now, infiltrated volume is equal to stored volume plus deep percolation volume. Okay. Now, out of the total volume infiltrated, some of it was stored as useful depth, okay, 100 millimeters, and then we also obtained its value in terms of volume, in terms of in meter cube, and deep percolation volume was also obtained. No, it was not obtained. We have to find it using this equation now. Okay, we already have the infiltrated volume. Now we will deduct stored volume from the infiltrated volume. Okay. Now V deep volume of deep percolation is equal to 57.93 minus 49.67. So volume deep percolation volume is equal to 7.63 meter cube. Okay. Now volume stored in percentage is 73%. Volume of deep percolation is 11%. Okay, and volume of runoff is 16%. Okay, so this is how we evaluate a border irrigation system. The stored volume was 73% and losses were equal to 27%, out of which 11% loss was in the form of runoff, in the form of deep percolation, and 60% was in the form of runoff. Okay.